So about us, so I was the first to hack the iPhone. I think it's this actual phone. I was the first guy to go down. I won't own. I wrote this book. Please buy it if you want. I make, I think, like 35 cents every time someone buys a book. And I'm into this no more free bugs thing. Although I think there's some arguments because I think there might be a free bug in this talk, but we'll see. Vincenzo.
Hi. Instead, I'm a student at Politecnico di Milano, and then I'm a security consultant for an Italian company, and finally, I'm sort of reverse engineering for Dynamics. That's all.
All right, so what we're going to talk about is some basic background stuff, and then Vincenzo will talk about his Userland exec technique that he talked about initially at Black Hat DC. Then I'll talk about Meterpreter for Mac OS X. Then we'll talk about iPhone security model and you know what there is we need to know about that, and then payloads for iPhone. Right, so this is the slide that's supposed to make you think why you care about this talk. So OS X is, you know, more people keep buying them. So this latest report says that about 10% of browsers on the internet come from OS X. There's some guy who did some game theory analysis that said that once it hits 16% of market share, that's when the bad guys actually care. So we're almost there. I don't know if that's good or bad. For iPhone, 50% of smartphone browsers in the U.S. where I'm from are iPhones, and 33% of the world's based on browsers. So that only counts the phones that are smart enough to actually browse the internet. And of course, girls like Macs. That's my personal study. That one wasn't from an official source. So there's been, you know, a lot of previous work on iPhone and OS X. So this is some of them. If you'll notice that most of these have to do with you know, getting a shell or something on, or techniques, you know, exploitation techniques. There's not a lot out there about payload, you know, techniques, and that's what this talk is about. So in this talk, we basically assume that you've managed to get EIP on OS X or PC for the device on the iPhone. And then the question is, what are you going to do interesting after that? So as much as we could, so we've integrated some things into Metasploit to make it easy to use. And then the part about iPhone is pretty interesting because there's things in it that I just discovered a couple days ago that no one really knows about yet. So you guys will be the first to hear. And then we'll talk about you know, in particular the newest version of iPhone that's out, which is 2.
Okay, so first of all, a brief introduction of my talk at Black Hat DC. I apologize if you can't get the full talk because I had to shorten the slides, but let's try to at least get the basics. First of all, we need to know what exactly a Metro file is. And Metro is the binary format employed by OS X. It basically contains 3 very important things. The first one is a header structure, which contains information about the CPU, the kind of architecture, and the number of commands it has inside, and that kind of fact. And an interesting thing about the header structure is that it contains a magic number that we're going to overwrite later in the talk, later in the attack. And then there are a bunch of load commands, which are basically used for symbol table location and the state of registers at the beginning of the execution. And the most important thing of a Metro file are segments, which basically are used to map stuff in the virtual memory, and they can contain from 0 to 255 sections that are the ones that actually do have the code inside them. And they also they can contain both code or data, and they have sort of protection flags like the Unix file system, in the sense that you can write, you can have writable permission on a segment, or readable or executable. Thanks, Charlie. And there's a representation taken from the Apple website. I hope they won't sue me. And as you can see, there is the header at the beginning, and then a bunch of load commands, and the segment commands which point to the rest of the file, which contains section data and that kind of thing. Okay. Since the relation between segment and sections is really important, let's try to do an example, a dummy example. As you can see, I hope you can see it. There is a segment, and it says that it starts at a virtual address 0 for 1000, and it occupies in memory 0 for 1000 bytes, and it's mapped at the beginning of the file, and you will take 0 for 1000 bytes from the file. I didn't mention here the protection flags, but the thing that you need to know is that section inherits protection flags from segment. So if a segment is readable, then all the section contained in the segment are readable too. And here's, instead of section, it says that it starts at 0 for 1D54 and occupies 0 for 275. And it starts at file offset 0 for D54. So as you can see, each section is contained in the virtual address and in the address of the segment in the file. And this is pretty important because, for example, the text segment, the one that holds the code, has a bunch of section for code, C strings, and that kind of stuff. Okay, thanks. So, what exactly is my attack? It's a Userland attack. It's not that new. In fact, it was introduced a few years ago in a FRAC article by the Greg. But there were a few implementation of it, and mainly they were for Linux, but without the randomization. So nowadays are pretty useless, and the most common thing, maybe the most similar attack to mine is the Meterpreter, because you can do the same thing. You can basically execute a binary in the address space of a victim process without touching the hard disk and without calling the kernel. You perform the whole thing in memory as using the user privilege on the victim machine. And it was presented as Charlie said, at Black Hat DC. And since a lot of people were sort of puzzled by the fact that I didn't show any real-world scenarios attack or that kind of demos, in this talk we're going to cover some sort of application of my attack, thanks to Charlie. And okay, first of all, I want to answer a few questions, the 3W. The first one is who can actually use my attack? And basically, on this point, there was a lot of misunderstanding because of the fact that a lot of people thought that it was some sort of mass ownage tool or 0 day or something like this. It's nothing of that kind. It's a post-exploitation technique. So you need to have a remote code execution on the machine in order to use it. Then what kind of attack is this? And it's two-staged in the sense that first you need to send together with the exploit a small payload, which is basically is really similar to a bind shell. And then we are going to send a crafted binary which contains a piece of code that I called the autoloader, which is then executed by the first payload. And so the magic is in these two pieces of assembly code. And the reason why you would like to do this is, first of all, it's a really powerful anti-forensic technique, because since you don't leave traces on your disk, you generally speaking, in some sort of forensic investigation, you're going to have a lot of troubles in finding my attack. And then I think maybe the coolest thing is that you can write your own payload, like in Python, Ruby, or wherever you like, then just compile it and send to the victim machine. And there are a lot more, but I won't talk about them now, because otherwise you just leave the room and Charlie will be disappointed with me. Okay, just another question. And what kind of binaries can you run? And the good thing is that you run every kind of binary, ranging from LS to Safari. And of course, in real life scenarios, you might want to just run network scanners, keyboard sniffers, and that kind of malicious code or stuff. So, in order to understand how a userland exec attack work, we first need to understand how exactly a binary is executed on OSX. So let's suppose that you want to run your own binary. What happens is that the exec VA system call is called, and the execution, as you know, is given to the kernel. The kernel basically loads the binary, it parses the commands, the segment that I mentioned before, and it maps them in the virtual address space of the process. And finally, it does another thing, that is to create a stack. As you know, an application, in order to run, needs a stack, and the first let's call piece of stack is created by the kernel. And after that, it happens sort of counterintuitive thing, and it is that instead of jumping to the entry point of the binary, the kernel jumps to the entry point of the dynamic linker, which is just a binary in a userland. So there are no strange privilege on the dynamic linker, and the dynamic linker loads the binary and resolves dependencies and links libraries and that kind of stuff, and finally it jumps to the entry point of the binary. Okay. And instead, what my attack does is to, first of all, we need to craft a binary, because the thing is, since we want to inject every kind of binary, we cannot assume that we have some sort of special code in it, like we are going to inject a bundles or a DLL as it happened for Meterpreter. So we need to modify the binary, and later I will show you a sort of infection technique that we use in order to put some stuff inside the binary. And the binary will contain a crafted stack, which is identical to the one that the kernel creates. And then the piece of code, the autoloader, which basically mimics the behavior of the kernel when it comes to loading a binary. And then we will send this binary to the victim machine. And finally, when the binary is on the victim machine, the autoloader is executed, and we also need to do some sort of cleanups of some libsystem variables, but I'm going to talk about it in a minute. And then we just jump to the dynamic link entry point as the kernel does. Okay, so first of all, the stack. How do we craft the stack? At the beginning of the stack, there is the base address of the Mecho file, and this is not common in between other Unixes. The reason why we need the base address of the Mecho file is that the dynamic linker needs to load the file, as I said before, and so the kernel just push it on the stack. And then we have all the command line arguments and environment variables. And then there is a nice string, which is the execution path that is used, for example, in tools like WebMap in order to show the path of the application. Like, let's say that you are running Safari, then the execution path will be /application/Safari/ blah, blah, blah. They are all padded, and then you have all the strings. So basically, the first thing that we're going to see are some pointers to strings at the end of the stack. Okay. And here's a representation. As I said, they are whole pointers, and then there are all the strings. It's a pretty standard stack, except for the address of the Mecho file at the beginning. Okay, and now how the autoloader works. As I said before, it's embedded in the binary, and once again, it impersonates the kernel. The only difference between the autoloader and the kernel is that the autoloader first needs to map the old binary. Since you need to keep in mind that we are doing everything in the process address space of a victim machine. So we first need to clean the process address space, and then we are able to map the new binary onto it. And this is exactly what the autoloader does. Okay, so here's a brief description. The autoloader just parses the binary, and it reads the virtual addresses, the one that I mentioned before in the picture of the segments and sections. And then it basically unloads by using some common API the segments that are pointed by the virtual addresses of the injected binary, and then it loads the new binary upon the address space of the victim's one. Okay, as I said before, we need some sort of infection technique in order to be able to craft the binary. And we use a technique that is called page zero infection technique. Later, I'm going to go a bit more into the details of this technique. What basically is contained in the page zero, the page zero is a segment that is contained in every binary on OS X. But if segments like the text segment, the data segment are useful because they store information, they store code, they store data. The page zero segment is useless in the sense that you cannot access it because it has no protection flags. You cannot even write to it, and it maps nothing from the binary. It's just reserve a blank page starting at virtual address 0 and ending at virtual address 0 for 1000, just before the text segment of the application. So we can easily mess it without creating problems for the execution. Okay, so basically the autoloader maps the crafted stack, and then it needs to clean the registers. And the other strange thing that we need to do is to clean some libsystem variables. I don't know if you know what libsystem is. It's basically the libc for OS X. And if we don't clean those variables, the injected binary will crash, and this is not something that we want. And finally, we jump to the dynamic linker entry point, as I said before. Okay, so since it might be a bit confusing, here's a picture. So here's the victim's process address space, and then you see a lot of blue segments. And here instead, we have a lot of orange segments. What happened is that the autoloader basically maps the blue segment and maps the orange segment upon the victim process address space. So the result is that we have our injected binary in the address space of another process. Okay, so as I said, here's how we infect a binary. First of all, the problem is that we have an autoloader that needs to be loaded by the first payload on the victim machine. And also we have a stack because, once again, in order to make the application run, we need a stack. So we have to find a place to store those two pieces of code and data in the binary. So we use the page zero infection technique. This technique was discovered by Nemo and another guy from VX7 a few years ago. So it's not that much new. And the other option that you have instead of the page zero infection technique is the cavity infector technique. What is cavity infector? I think that I forgot to mention before is that segments need to be page aligned. So even if you need only just few bytes, you still have to map the whole page for the segment. Otherwise, the binary won't run. The cavity infector is a way to store data in the slack space of the pages of a segment. So let's say that your segment takes 100 bytes. You still have to map 1000 bytes. So the rest of the bytes are just 0. And you can, by using this cavity infection technique, you are able to write some code or data in it. But since it's a bit more tricky to use this technique, my first implementation of the attack was based on the page zero infection technique. So we are just going to talk about it. So what we do is to change the page zero protection flags, the one that I mentioned before, the writable, executable, and readable permissions of a segment with a custom value. This is just because when I had to write a bit of assembly, and instead of comparing strings, like instead of searching for page zero, I wanted a easier way to find the stack that is contained in the page zero segment. So I just use a custom value, but it has no real utility for the attack itself. And then we store the crafted stack and the autoloader at the end of the binary, following the rule that segments and sections need to be page aligned. The other thing is that we point the page zero, like the virtual address, the file size, the file offset, and that kind of stuff to the stack, so that when we reach the page zero segment, we know exactly where we need to map the stack, because of course the stack needs to be mapped at a virtual address. How big is the stack, and that kind of thing. And the last thing that we do is to overwrite the first bytes of the file with the address of the autoloader. And about this thing, the fact is that, as you might know, now Apple has a new binary format, which is the FAT format, universal binary format. In this talk, we are supposing that instead we are using the Metro file format. But this doesn't mean that the attack doesn't work on universal binary, because universal binary are just a bunch of Metro file included in a single file. So the thing is that we need to overwrite the signature, the magic number of the binary with the address of the autoloader, so that when the shellcode is executed, and receives the binary, it knows exactly where the autoloader is, and it can jump to the autoloader address. Okay, so here's the binary, the layout of the binary after the attack. So the header points to the shellcode, and the infected page zero pointed to the crafted stack. The rest of load commands and segment and everything else stays the same, which means that, as I said before, since you don't create any kind of problems to the binary itself, you can basically inject every kind of binary, because both LS and Safari shares the same layout, and we don't touch any critical information for the application. Okay, so here's a picture of how the attack is supposed to work. The first thing is that the attacker sends to the victim machine the exploit plus the payload, which is the bind shell that I mentioned before. And the bind shell opens a connection on the victim machine, and the attacker sends the crafted binary, which contains the autoloader. Then the autoloader is executed, and eventually, if needed, the output is redirected from the victim machine to the attacker machine. Okay, I said a few times that we need to clean some libsystem variables. The reason was that otherwise the program would crash. This is the slide of bad news about cleaning the variables that we need, because they are not exported. So we cannot use any sort of dlopen, dlsymbol combo. Dlopen, okay, just to clarify a bit, dlopen and dlsymbol are two call that can open a library and loads a symbol, but this works only for exported symbols. Since the symbols are not exported, we cannot use this sort of trick. And the other bad news is that the other space layout randomization is employed for libraries on OSX. even if the implementation is a bit flawed, it still makes that thing not non-trivial. But here's instead the slide of the good news. First of all, the dynamic linker has a list of the linked libraries. It means that if a binary needs to have libsystem, libmath, lib wherever you like, the dynamic linker needs to know about it. The second good news is that we can access the list by using some calls that are exported by the dynamic linker. And two things that I didn't wrote in the slide are the fact that the dynamic linker is not randomized, and this is a big failure for Apple because, okay, you can randomize libraries, but if you don't randomize the dynamic linker, I can still get to the libraries. And the other good thing is that the dynamic linker needs to be in the address space of each process, so we are able to reach the dynamic linker from every binary. The idea of the whole attack is to perform everything in memory, because the address space layout randomization on OSX relies on a file that is stored on the file system, and this file contains the new address of the libraries. But since we're trying to do everything in memory, we just use those functions exported by the dynamic linker.
So one funny thing about this, I think, is so the ASLR that's in Leopard, it doesn't randomize. So it randomizes where the libraries are. It doesn't randomize where this particular guy is. It doesn't randomize the stack. It doesn't randomize the heap. But of course, when they produced Leopard, they said Leopard has ASLR, right? And so now Snow Leopard is gonna have real ASLR, right? So I can't wait to see what their marketing guys come up with to say they can't say new feature Snow Leopard has ASLR because they already said that once. So I can't wait to see what they say Snow Leopard has.
Okay, so here are the function that we use from the dynamic linker. They are basically used to retrieve the base address of a library, retrieve the name of the library and the number of the library. The thing is that we can just iterate through the libraries and search for the one that we need. In our case, libsystem. And once we found the library, we can get the base address of the library in memory, and that way we have basically defeated the address space layout randomization. It's pretty easy. But first of all, in order to run those calls, we need to find them. So what we do is to parse the load commands of the dynamic linker, which is just a standard material file, standard binary, and we retrieve the address of the linked segments. The linked segment contains the symbol table for a binary, and if the symbol is exported, then in the address space in the virtual address space, you're going to find the symbol address. So we basically iterate through the symbol table of the dynamic linker and the search the functions in linked. So now we have retrieved the address of the function, and we are able to call them. Okay, so now we are back to the libsystem problem. Non-exported symbols, as I said before, are taken out from the linked segment. So in memory, we are not going to find a non-exported symbol. And this was sort of disappointing for me, because the only way to solve this problem was to open the libsystem binary and find the variables in the symbol table on the binary, and then we just adjust those variables address to the base address of the data segment of libsystem. So let's say that one of the variable is stored at address 041D54 in the binary, and since the library is randomized, instead it should be stored at 04A543. What we do is just to adjust the real address, so we are able to clean to zero the variable that we need to use. Okay, the results. The first thing, as I said before, is that you can run an arbitrary binary on an arbitrary machine, and then that you don't leave any traces on your disk. You don't have to call the exact VA, so basically the kernel doesn't know about us, and these 2 points are really useful for an anti-forensic point of view. And once again, it works with every binary. I think the coolest thing is that you can write payloads in Java, Python, Ruby, every other high-level language. Another thing that happened during my talk at Black Hat DC was that I didn't show a shellcode to people, and they thought that okay, but the shellcode is too large to be injected together with an exploit. And this is basically not true, because as I said before, it's a two-stage attack. So the first shellcode, which is the one that needs to go with the exploit code, is rather short. It's just a few bytes more than a normal bind shell. And here it is, as you can see, it's no big deal. And here's a demo.
Let's see if it will actually work. I'm cheating a little. So my computer crashed like 10 minutes before the talk. So how about recover? So you want to say what's going on here? So this window is supposed to simulate a process that's been exploited, and it has the shellcode that we showed you, something like the shellcode we showed you running. And then this window is the attacker, who can then connect to that port that's now open on the machine and send it the modified binary, which in this case is the calculator program. So there it is. It wasn't there before. Trust me. And then just to see even more, if you don't believe me. So if you do a PS, this is the guy here, and so for some reason the process listing.
For some strange reason, the process name in PS is sort of messed up. But if we run a webmap on the PID of the process, you're going to see that the guy that we are running is actually the calculator and is not our testing program. So what happened is that we just mapped upon our testing program, which was that one, the jumper, the calculator segments, and now we are able to run the calculator as if we were running the jumper. It's pretty straightforward, I guess, and I hope.
Okay. And then another one. This one is just if you really want to believe or not that shellcode works. So there it is.
The shellcode that I showed you before, and
so then I'm just running it, and this may or may not work. Let's see. And then here, instead of calculator, this time we're running ls. All right. So this stupid test program binds to the port. We'll try it in like a minute, and it'll work.
Yeah.
So right now it can't get that port. 1, 2, 3, 4, 5. Work now.
Okay.
Okay, there. So now it ran ls over here. So there we injected. So in one of those injected calculator, which is like it's not huge or anything, but it's a big program and it's GUI and all that stuff. And then the other one we did ls. So there's you know like Vincenzo said, in real life you would be injecting like some big tool you wanna run, or like a keyboard sniff or something. All right, so that's one thing, one interesting payload you could do. Another one is Meterpreter, and these are both for OSX so far. We'll get to iPhone in a little bit. So what's Meterpreter? It's part of Metasploit, which is a open source exploit framework. The idea is you just bring along everything with you, so you don't have to trust whatever's there. Maybe they don't have the program that you want, so you just bring along all your tools. It's stealthier, so normally if you just pop a shell in a box, so bin sh is running, and then when you start typing commands, you type ls, so that forks and execs ls. So in a process listing, you see all that. Here, everything runs inside of Meterpreter, which is running inside of the exploited process, so it never forks, it never runs anything else. So and also it never touches disk, so you don't see the Meterpreter sitting on the disk. So hopefully it's going to be a little harder to know what's going on. It's modular, so you can write modules for it and upload them. So maybe you have a module that has some local privilege escalation or something, and it can also do stuff that a shell can't do. So, for example, if you pop a shell in a box, it might be sort of a pain to upload a file or download a file. Well, this does it automatically if you want. You can edit files. You can also do what's called pivoting, which I'll talk about, which is redirect attacks through that box to other boxes. So it's a way, once you have a beachhead inside a network, you can hit the other boxes that are inside that intranet. So here is a picture of pivoting, and I might show a demo of this if we have time. So the talk's a little long. We might run out of time at the end. And I'll explain why it's long, actually, at some point. It's interesting. So how's pivoting work? So say I've attacked through the firewall this guy on the right. This guy. So I now have a socket open to him. So what you can do for pivoting is you open up a port on the attacking box, such that whenever you talk to that port, it gets funneled through the existing channel, and then you can send stuff out into the internet there. So you can imagine maybe there's an internet web server that has some vulnerable web applications. So you surf to this local port address, and it ends up surfing out of the exploited box to the some new box, and you can do that on any port you want. All right, so I was like really into Keynote automated slides for some reason for a little bit. So how's it work in Windows? How's Meterpreter work? Well, Metasploit, it has an exploit, of course, that it gets you on the box. And then the payload uses the DLL inject payload, and Meterpreter is just a DLL. So the main Meterpreter is just a simple DLL. So now that's running inside the process. And then you can upload additional modules, which are also DLLs, into the process, which then enables the corresponding Metasploit code on the other side. And then one of the things Meterpreter does is it handles channeled communication, so then you can talk to it over that. Yeah, well, you can do the same thing, of course, on Mac, and that's what I did. So I ported this code to Mac OS X, and the main differences are, instead of injecting DLLs, since obviously they don't have DLLs, is I inject bundles, which are basically Mac OS X dynamic libraries with some extra resources and stuff. And the actual functions I use to do this are these two big API functions, which are actual Apple APIs. They're deprecated, but they work. And it's designed, I don't know why they have them, but it's for us, it's designed to load, you have raw bytes in memory into, a library. So it's exactly what we want. It doesn't touch disk, so that's good. And if you run VMmap on the process, it doesn't show up there either. I don't have any idea why, but it doesn't. So that's good. The first bundle that you upload, the main Meterpreter or Macterpreter in this case bundle, all it does is it allows you channeled communication and it allows you to upload extensions. It's kind of dumb. It doesn't really do anything. And so the good thing about that is it shares almost all the same code with Windows. And this should be and if you download Metasploit right now, it should be in there. And so like I said, so it shares most of the source code. So hopefully when people update the Windows version, they'll update this one too. So what's a bundle look like if you want to write some code for it? Well, basically it's just something that has a constructor, a destructor, and then the inject bundle payload specifically looks for a function called run that it's going to call. All right, so this is just a little more details. So how does this work on Mac OS X? I described it for Windows before. So first there's a little bit of shell code, which basically just it just binds to a port and then it expects more shell code that it will run, and that's like 250 bytes. Then there's this inject bundle payload, which expects to receive a bundle, and then it will call those two API functions to map it and then link it, and then call the run function. And then after that, you can upload whatever bundle you want. So again, you get the advantage of being able to write your shell code, in this case, in C or C++ or Objective-C or whatever, and you can make it as complicated as you like, and you don't have to write assembly anymore. And also it's not going to touch disk. Right, so the main Meterpreter DLL, it's sort of pointless if that's all you had, but the good thing is then you write these extensions. And so I wrote this extension called Mac API, and it basically has the same stuff that the Windows standard API extension has. So it's got stuff to work with the file system with. You can make directories in LS and upload and download files and that sort of thing. It's got that pivoting I talked about, so you're able to just automatically attack other hosts from the already exploited host. Process stuff, network stuff, and then some other unusual things like, so you can reboot the box, or you can get information about Mac OS X version that's running. And another cool one is you can take a picture of the guy who's sitting at the computer if it's a MacBook. I'll demo this in a minute. It's sort of fun. So what's the limitations with this? Well, one of the things I haven't mentioned yet, but it's true, is that I wrote it such that the existing client, the Metasploit client, could talk to the Mac one too. And so part of that is I have to be binary compatible, so I have to send back the same data it expects when it asks for directory listings. And like running dir and running ls, you get different information. ls gives you more. So I don't send that additional information. I only send what it already expected. Another thing that Metasploit can do that I can't do on Mac OS X that's pretty cool is in Metasploit you can migrate your whatever process you're in, you can go to another process. So maybe the thing you just exploited is sort of unstable and you want to get to a new process. You can't do that in OS X because, and this is one case where it's actually more secure, typically processes don't have permission to inject themselves in other processes, even their own children. So the way GDB works is sort of a hack. It's if you ever look, it's set GID procmod, and that's what gives it the reason, the permissions to do that. And then there's other things that I was just too lazy to do. So let's see a demo real quick. All right, and so this is a Linux VM. So, and the reason I'm doing it in Linux is the Ruby so Metasploit is written in Ruby, unfortunately, for me at least. It doesn't, so the client doesn't work so well on Mac OS X because the Ruby for Mac OS X is kind of not so great. So I'm running the client from a Linux box, and then the server guy that it's going to exploit is right here. And this is just, this is a talk about post-exploitation. So this is just a dummy server and a dummy exploit.
We don't give away free bugs, do you remember? So that's the reason why we use dummy programs.
So let me see if I can make this a little bigger for you. Control plus. Okay, so now I have a Meterpreter session. I don't know if you can read that very well. Try one more. Okay, so then I can start running commands on it. And again, none of this is, I run ls here, and it doesn't show up as an ls process. These are the all the different commands that are implemented, although you can't really see them. But I'll just run through a few of them so you can see. So, you can get directory listings, although again you can't really see it, but it's there. You can read files. Oops, shoot. Hold on. It works better when your screen resolution isn't gigantic. Right. All right, so there's that. So I just read that file. I can get, it's all the stuff you would want to do. You can do, and then you can get Mac OS X specific stuff. You can if you missed the day of actually having an actual interactive shell, you can do that too. So you can run other programs, either ones that are already on disk there, or ones that hold on a second. Or you can upload one and run it. Shift Control C. So now I have, like, this is like the old school remote shell. And then you can do, like, oh, hey, I wonder, if it's like, some big guy without a shirt on whose computer I just owned. So, right. All right, and then, so it takes a picture, and then you can have it download the thing, but right now it just sets it in temp, which isn't very stealthy, but, you can fix that. It's all open source. So I'll download that file. I mean, it's not that I'm lazy, it's that I wanted to show how you can download files. JPEG. Okay, so then we can watch it over here. Let me So this is the picture I just took of my victim. If it comes up. Oh, here we go. So there I am. Look, it's even an action shot. My hand's moving. Okay. So what else can you do? So here's the command if you want to do the pivoting. I'll skip that because we're running late on time here. One more thing. I'll just leave it. Okay. We'll come back to that. Okay, so that was if it didn't work. So the other thing is I took Vincenzo's payload and I put it in Meterpreter. So you can do userland exec, which means you can upload binaries and run them all in memory without them ever touching disk and without them, that's the main thing, so they don't touch disk. And so let's see that while I have the demo up here. If it's still active here. I don't need you. Okay, so here's the command I want to run. So basically I've, in advance. Okay. So what I just did was I prepared this, created binary that has the autoloader built into it for LS. I uploaded it, ran it in memory, and then I got the input and the output over the Metasploit channels. So you can see that within Metasploit, I was able to see the output of the LS. And so you get the output of Nmap or whatever you want. So it's pretty cool that it all happens, automatically, and like script kiddies can have the fun that us people usually get to have.
Okay, so let's go quickly through the security architecture of iPhone.
All right, so let me just say something else real quick. So one of the reasons this talk is like too long right now and actually different than if you read what it was supposed to be about was I got involved with Vincenzo on this because I thought the userland exec thing was pretty cool. I was like, well, we should do that on iPhone. I did it on my jailbroken phone and it worked and it was really cool. And then a little while ago I figured out that hey, it didn't actually work on the factory phone. And so that's what this part is about. And so we had to change our talk because this talk was gonna be like, okay, here's userland exec for OSX and then for iPhone. So then I was like, no, it doesn't work. So we have to hurry up and change it. So now it was like, okay, now it's gonna be OSX, userland exec, and then like other cool payloads for iPhone and stuff. And then as we'll get to, so a couple days ago I figured out you could probably do it.
Yeah, and then there's the part why it doesn't work on factory phones.
So now we have three talks sort of into this one talk, three evolutions of the same talk, and so hopefully we don't run out of time. We're going to do some sort of compare and contrast between OSX and iPhone. So the first thing is address space layout randomization. On OSX, as I said before, is employed for a library. For libraries, but it doesn't randomize the heap, the stack, and all the useful thing. And instead on iPhone, there is no address space layout randomization, where there's no big difference. I mean, the one employed on OSX simply doesn't work, so they are on the same level, basically. And the addresses on iPhone relies only on the firmware version, like in all 2.0 firmware, the addresses are at a fixed, the addresses are the same and so on. And the other thing is the non-executable bit on OSX.
is set only on the stack, so we can write on the heap. We can change permissions on the heap without having any kind of problem. And also the cool thing is that heap may have pages with all the protection flags set, so we can write, read and execute a page on the heap. Instead, on iPhone, things are pretty tough, because starting from ARM version 6, there is an execute never bit, and both the stack and the heap are protected. No heap pages can have all the privilege at the same time, and the worst part is that non-signed page that was ever readable can never become executable. This means that if you have a page of the heap and you can write to it, you will never be able to execute it. So, except for one case that Charlie discovered 2 days ago while he was at the airport. So, it's pretty difficult or impossible to inject code on factory phones. And once again, except for the case Charlie discovered. And this is the worst part. So, the code signing, the famous code signing. All library and application needs to be signed by Apple in order to run on factory phones. The cool thing is that both OS X and iPhone share the same code for code signing. So we were able to just read the code of the OS X kernel and see how the iPhone behaves. And the reason why we did this is that by using bindiff, and this is sort of promotional campaign, but it's pretty cool because we were able to do cross-platform diffing, and so we were able to see that the OS X kernel and the iPhone kernel share a similarity of 0.65, which is pretty huge if you consider that they have a lot of low-level stuff. And the code signing part, in particular, has a similarity of 0.74, which is really high. And I hope you can sort of read it. This is a screenshot from bindiff, and as you can see, these are the structure, the call graph structure of a function used by the code signing infrastructure. And as you can see, they are basically very similar. So we are safe to say that we can perform our analysis on the source code of OS X instead that using the binary of the iPhone kernel.
Keep in mind, one of those is x86 code and one of those is ARM code.
Yeah. Okay.
Sorry.
No problem.
We're in a hurry.
Go ahead. Okay, so let's say a few facts about the code signing protection. When you call execva, as I said before, when you want to execute a binary, the kernel search for another segment. So apart from doing the whole thing that I mentioned before, it checks for a special segment which contains the signature for a binary or for a bunch of segments inside the binary. If the signature is already present in a list maintained by the kernel, then it is validated using hashes and offset, which means that we cannot use any tricks like the cavity infector that I mentioned before. We cannot write stuff in a slack space of segments because otherwise the hashes won't match. Instead, if the signature is not found, the signature needs to be validated, and once again, it needs to be signed by Apple, and then all the other stuff are done, like validating the hashes and the offset. So they did it in a pretty good way. Once again, hashes are calculated on the whole page, so no cavity infector technique is possible. So, what exactly is the effect of code signing? It's pretty simple. When a page is signed, a flag, the signed page flag is set. You might wonder, okay, but who cares? I mean, we are not touching protection of any sort. So the next question is, what happens if I don't sign a page? We can still map a page, but we have to follow the execute never beat policy with read and execute permissions. But whenever we try to access a page that is not signed, the program will simply crash. And also, if we try to change the permission of a page to, for example, enable the execution, the call fails, except for the case that Charlie will talk about in a few minutes. So the next pretty common question is, okay, and how about libraries? We cannot load any libraries from memory because on the iPhone they taken out that part from the dynamic linker. So we just can open a binary. We can just open a library from the file system. What happens is that when the library is opened, a special syscall is called with a command of f_add signature, and as you can, and the signature itself. So basically, we run the same check as for executable, but using a special system call. And if the signature is found, then the signed bit is set on the pages of the library. Otherwise, the program will crash. And here's the function. Once again, is bindiff. Here's the function that loads a library from the file system. This one comes from iPhone, and instead this one comes from OSX. I don't know if you can read it, but the only difference is that on iPhone there's an extra call, which is a function named load code signature, which basically does what I mentioned before, the special system call. Okay. So,
want me to talk about this?
No, well.
So quickly, so what's the history of iPhone research? And this is sort of the new stuff that no one really knows about. So in version 1 of iPhone, it was like there was no protections at all. Like everything ran as root. All the pages were read-write executable. It was great. Version 2 came out, and people noticed right away that you couldn't have read, write, and execute pages. But on jailbroken phones, you could first read and write, and then you could change that to read and execute, and then you could execute it. So like you could do shellcode. It seemed like you could do shellcode and stuff. And you could, for example, do userland exec pretty easily. However, I noticed, as I mentioned before, that when I was testing stuff for this talk about 3 weeks ago, I noticed that, hey, you can't actually do that on the jailbroken, on a factory phone. So you can't go from read write to read execute. It doesn't let you do that. And I wasn't the only one to make this mistake. So if you look back at CanSec West, which happened a couple weeks ago, there's 2 talks at least that either implicitly thought that they were talking about jailbroken phones or didn't realize this either. And so they talk about, the way you execute shellcode is you just return into mprotect and change it to be your shellcode to be executable, jump into that, and you're good. That doesn't actually work. So then there was a couple weeks of us like frantically figuring out, well, what the heck are we going to talk about, right? And so there's a whole part of this talk where I'm not even going to talk about, but it's in the white paper that Black Hat has about, well, you could do return to libc still, and you could just do everything you want in return to libc. But like Vincenzo mentioned, so 2 days ago though, I figured out that you could actually, through one slight little trick, get your shellcode to execute. So you can mess with the page permissions just enough that you can get your shellcode to be executable. So here's just this again. So again, so there's talks out there that say you can do return to mprotect. You can on jailbroken phones. You cannot on factory phones. And here's what happens if you try to run it on a factory phone. So copy your shellcode, call mprotect, then jump to it. Permission denied, can't do that. And you can see it jumped to actually the exact address that it said, but it died because it wasn't executable. So the mprotect fails. Well, that was on the stack, so maybe it's just, they got it right on the stack, but nowhere else. Well, what about the heap? Okay, so instead of the stack, so I call malloc, I call mprotect to make it now executable, I jump to it. What happens? Same thing, right? It says, your call to vmprotect fails. You cannot do that. And, again, it crashes when it jumps to the heap buffer, because it's not executable. Well, another idea is, what happens if we take code that's already executable and we just modify it, right? So at least the page permissions are sort of right. So maybe I can do that. Well, that doesn't work either. So you have an address. This is just some function in my main binary. I say, okay, I'm going to try to make it writable because I want to write my shellcode there. And then I'll copy my shellcode, and then I'll execute it, or I'll change it back to executable, wherever I want. But as soon as you try to change it to be writable, it says, nope, sorry. I know that this is executable code. You're not going to be able to change it. It's, it's already signed and what have you. So nothing works, right? And so this is where we were. This is the state of the art of iPhone research 3 weeks ago. But what about this? This is the state of the art of iPhone research 2 days ago. So what if you take shared library code and then you try to make that writable and you make a virtual copy of it? What about that? I don't know. Let's see. So you take an address. This is just the function getchar, right, from the C library. I tell it, I want to change the permissions to be read or writable, and this says, I know this is shared between different processes. I want my own local copy. And I think that's basically the bug, if it's a bug, is they forgot to check this one little, one case. Then I copy my shell code and I execute it. And then just to prove to myself that I'm really executing my code, after that I have a null pointer to reference and a print statement. But I didn't even trust my print statement. So my shell code in this case, it fills the registers with 1 through 6 and then infinitely loops on itself. Oh yeah, it actually worked. Cool. So you see the VM protect worked. So it did allow me to change it to be writable. And then it just sat there in an infinite loop. So I Control-C'd it. I saw where I was. It thinks I'm in getchar, which obviously I'm actually in my shellcode. And then I look at the registers, and sure enough, they're set. So you can actually do this. You can get so no one thought for the last month you could actually get shellcode injected into the process and run it like they have like perfect depth. But it turns out it's not perfect. You can do it. So the way you do it, and this is on the latest version 2.2.1. The way you would have to do this in a real attack is you'd have to do a return to libc first to get your task. And then call VM protect, do it using the exact flags I just mentioned. Then you would have to return into memcopy to put or you could just do it by hand or something, I guess. But you'd have to get your code into this region that's now writable and executable, and then you jump to your shellcode and you're done. What do you want to do for the last 5 minutes? I think we keep this part. So I guess you want to mention this for a little bit, and then I'll take back over when it.
Okay, so one other important thing about the iPhone infrastructure, security infrastructure, is sandboxing. Application from the App Store run in a sandbox. The concept of sandbox is pretty simple. It's a way to limit the thing that an application can do. It used the same, once again, the same code that is used on OSX, the seatbelt module for the kernel, and a sample for a sandbox can be found here if you have a Mac. So
actually, an iPhone.
iPhone. Yeah. So here's a bunch of information. For example, you cannot write any file. Or let's see another cool. You can fork your process and you can execute a process. So you have sort of rules for the application itself.
And this is the rules that all the programs that you download from the iTunes App Store follow. So they can't fork. They can only exec certain things. They can only write certain places, read certain places.
So outside the sandbox, you have other applications like Mobile Safari, Mobile Mail, Mobile SMS. They are not in the same sandbox of the App Store applications, but they still are in a sandbox, even if it's less restrictive. Yep.
So this is the one, in my opinion, one of the cool things about this talk is breaking DEP on iPhone. The other is that no one else really seems to know that the Apple apps actually run in a sandbox too. So here's an example of Mobile Safari sandbox. So I inject code by using GDB. So I try to open up the SMS database. Yes, I can do that. I try to run fork. No, I cannot do that. And then here's what you see if you in the kernel dmessage. So when you load mobile Safari, it says, okay, I'm using a built-in profile. That means it's built into the kernel. It's not something that's sitting on the file system, so it's hard to figure out what it is. And then here it is when it denied me trying to fork. And one interesting thing about not being able to fork is that on OSX, if you can't fork and you're multi-threaded, you can't exec either. So traditional shellcode that just execs bin.sh won't work if they don't let you fork. So that's one issue. What should we? Let's do like this slide, and then we'll be done. 2 more slides, and then we quit, and then we'll talk about it.
So the differences between jailbroken phone and factory phones. The jailbroken phones basically disable the code signing protection, and so the signed bit that I mentioned before is ignored, and so it's possible to use some sort of return to unprotect technique. And the thing is that nobody noticed that. In fact, any previous talk about iPhone assumed that you were running on a jailbroken phone, and this is something that we discovered it when we had the problem with the Userland exec. Okay, so for example, here's a patch for the jailbroken phone. As you can see, the max protection flag is not that is usually set on the factory phone is not out by the jailbreaking patch. So here's a few things that the dev team did.
All right, so you might think, oh, my jailbroken phone is just like a real phone, except I can run signed things, but part of running signed things is all this memory protection stuff. All right, this is our last slide, I promise.
Okay.
So basically, then the question is, well, how come all of us researchers were so stupid that we never actually tried this on a real phone, right? And the reason is it's really hard to test things on the real phone unless you have a 0-day, which I don't happen to have. So the only way you can get programs running is through the iPhone SDK. And there they run in that really restrictive sandbox you already saw, and you have to pay $99, and the GDB is a real pain in the butt. So that's why people didn't actually try this out. So we have a white paper that is available about the stuff that we skipped, which is basically how you could do return to libc even if you couldn't have shellcode running in the iPhone, but having shellcode running in the iPhone is way better anyway. Also will be available afterwards in the little discussion room if you want to learn more about that. Or send us an email. We'll send you the slides on everything you missed. So you missed this section called Factory iPhone Payloads. But it's more important, I think, to see that you can actually break the dep, and then you can run any old payload you want without having to worry about it. That's it. We're out of time. Thanks.
Thanks.